So now we're going to take a look at how do we convert a geometric vector into an algebraic vector, and then how do we use these algebraic vectors, and when do we want to use algebraic methods versus the geometric methods. Okay, so we're going to be taking a look at the exact same two questions that we did before, and we're going to compare the answers. Okay, as far as not the actual answers, but the method, which one's more efficient, okay, in different situations. But we first have to say, how do we convert geometric vector into an algebraic vector? And what it's called is resolving a vector. Okay, now, for those of you who have already taken physics, all right, you've resolved a vector before, all right, this is almost the same method. Almost the same method, okay? Just gives you, it's going to be slightly different, all right? But anyway, bear with me and let's take a look and see what we've got. All right, so first of all, what we're going to look at is we have this vector r, all right? And we're going to say it has the components AB. It makes a certain angle, all right, with the positive x-axis. The angle, the positive x-axis, all right? Now, when you take a look at the diagram itself, all right, so we're looking at the diagram itself. You can see that we've set up a right triangle, all right? And if we're looking at the magnitude, okay, of r as the length of the hypotenuse, you can see that the A component, right, the A component, the length of the adjacent side to the angle, all right, gives us cos theta is going to be A divided by the magnitude of r. All right. If we look at then the B component, okay, the Y component in this case, right, the length of B, you can see that it is opposite the angle. And so we have that sine theta is B over the magnitude of r. Solving for the components A and B, you can see that the components for r is the magnitude of r times the cos theta and the magnitude of r times sine theta. Okay, that's how you resolve a vector. All right, now the small difference between this vector method and what I believe that you were doing in physics, all right, is we're not looking at related acute angles at all. All right, what we do is we take a look at theta being the direction angle of r. It is the smallest non-negative angle with the positive x-axis. All right, what I mean by that is if we're looking at a vector over in the second quadrant over there, we deal with theta as theta is. We don't worry about the related acute angle and say what has to be negative and positive and whatnot. If we get the full angle, maybe it's 120 degrees or whatever it is, then our calculator will give us the negative and positives that we need. Okay, and it's right there. So as an example, all right, if we take a look at this missile question here, it's heading on a bearing of 300 degrees at 750 kilometers per hour. Express this as an algebraic vector. Well, first of all, let's take a look at what a bearing is. All right, bearings, all right, start at north. Now, they don't say north, right? They say that's at 0 degrees. North is 0. And what they do is they travel clockwise until you hit your degree. This would be a 300-degree bearing. Okay? 300-degree bearing. That's what you've got there. All right? Now, since we're looking at resolving the vector, we have to go with the smallest non-negative angle that is from the positive x-axis. So you've got a full 90 degrees plus another 60 in here, right? So that is 150 degrees. All right. The velocity 750 kilometers per hour. So that means our missile is 750 times the cos of 150 degrees, and the y component is 750 times the sine of 150 degrees. Okay? Now, you calculate that out, what you've got in here, notice when we do the speed, there's our velocity right there. You automatically, the x component is negative. You can see it's in the second quadrant, right? The y component, that's positive, right? Yep, second quadrant right away. All right. So if we look at this direction angle as is defined here, all right, our calculations will automatically give us the positive and negative portions. All right, so it's one thing to try to get used to. I'm not going to force anybody to do it that way, so long as you resolve a vector correctly. All right, either using this method or using the method that you did in physics class, it's fine with me, so long as you get the right answer. Okay, so let's move on and take a look. Now, the idea with doing the same questions again is, which method is more efficient? All right, and you're going to be doing similar questions, if not the same, for the homework too, but I want you to do them in this algebraic method to see which method is more efficient. Okay, it will change depending on what information that you have, all right, and what you don't have. Okay, so again, taking a look at the example that we have with the linebackers, all right, they're hit. We've got a 350 east. All right, let's take a look at that one first. Now, resolving this one first is pretty simple, actually. There's not a lot of calculations to it. We know it's 350 newtons east, okay? Well, it's right there, 350. How do you get that along the x-axis, right? It's pretty simple. You got 350 along the x-axis, 0 along the y. Right? If you worry about a 0-degree angle, you'll get the same result. All right, let's take a look at the more interesting one. How do we resolve the 200 northeast? Okay, we know that northeast has an angle of 45 degrees, right? And so when we look at the smaller linebacker here, we'll just call it S for the smaller linebacker, right? We've got the magnitude times cos of the angle, magnitude times the sine of the angle. Okay? So when you have those two, so 200 times the sine of 45, or times the cos of 45 degrees. Right, oops, where are we here? 41, 42. 200 times the sine of 45, 140, 142, right? Because they're the same. All right. Now here's the thing. How do we get the resultant, right? If this is the larger, we'll say that's the larger one there. The resultant is just adding those two vectors together, right? You've got your linebacker going this way, the L, you got your linebacker this way, the S. That's just adding the two together. So we know all we have to do is just add. So the resultant, QB, the Q, let's say, is when we add 350 with 141.42. So that is 491.42. And then 141.42 for the Y. There's our vector, right? What we don't know is the magnitude of that, but it gives it to us in there, right? We can see what the magnitude is. In there, we can calculate it. We know that the magnitude, right, is the square root of the x squared and the y squared. Right? So you take out your calculator and you start to do the work. 491.42 squared plus 141.42 squared. End your bracket, and you get approximately 511, right? I get a 3.6 newtons, okay? What about the angle, right? What about the angle here? Well, we know that we're talking about the angle with the horizontal. It was set up that way, okay? We know we've got the x and the y opposite, adjacent. We use tan. Tan of theta equals the opposite, 41.42, divided by the adjacent, 491.42. All right, we take the inverse of that. The tan inverse, 141.42 divided by 491.42 gives us approximately 16 degrees, right, from what we want. So again, we have the exact same answer that we did before. Now, if we were to compare the two answers, maybe with just these two vectors being added together, it may seem almost the same type of work, the amount of work. But what if we were to add a third vector on? Okay. What happens if three people basically gang tackle this one? Well, geometrically, you'd have three like this. And you'd have to work out this one first, and then you'd have to take the one you just did, add it to the third one, and then work that one out and do all that work again. But if you did it algebraically, resolve the three vectors, 1, 2, 3, add them together, and you'll have your resultant. Okay? If you have the initial vectors and all you have to do is add them together, I think algebra is much more efficient. Okay? Much more efficient, especially if you have more than two vectors being added together. Okay? So try your hand at that. All right? Now, let's take a look at the scoreboard and do that algebraically. All right? And let's see what we have to do here. Scoreboard again, just to refresh our memory, two cables make an angle of 35 and 40. The scoreboard has a weight of 350 newtons. Okay, so the 350 newtons is going down this way. Draw the diagram to understand the situations where we see these two. And to make it algebraic, we take a look at putting it on the grid. Line it up, see where all the angles are, right? Now, we can see with cable 2 that it's 40 degrees. Theta is 40 degrees on this side. We'll call it theta 2, right? Because of the Z pattern. We can see clearly the Z pattern there. For cable 1, right, using the Z pattern to get the 35 degrees down here will then give us the 145 degrees all the way to it. So our theta 1 is 145 degrees. All right. Now we can resolve. Now we have to resolve the two vectors. All right. And notice that when you add those two vectors together, you're going to end up with 350 going up high, right? All the way to the top here, 350 in the opposite direction. Okay. 350, I'll put this out, north, right? In this case, it's north, the positive. I'm going to put it like this. You can see the resolving that one. Has to equal basically cable 1 tension plus the cable 2 tension, right? Whatever the components are. Well, let's take a look at what the components are. We see cable 1. We don't know what the magnitude is, but we do know the angle. All right. Cable 2, we don't know what the magnitude is, but we do know the angle, right? Since we already know the scoreboard is going down, and I already talked about it, then the equilibriant, okay, is going to go up. So the equilibriant, maybe if I change that to an E to make equilibriant, then that's why we have the plus 35, okay? So in this case, if you're looking at it following along, the equilibriant is equal, right, to the C1 plus the C2. So we have to add the components. And by looking at it like this, we can add them vertically, right? C1, magnitude of C1 times the cos of 145 degrees plus the magnitude of C2 times cos of 40 is equal to 0. Take a look. Okay. Let's see what we've got down here. Look at the two, right? Here's the equal 0 right there, the one we just did. The y component, to get to the 3,500, you add the y components together. And look what you come up with. You've got two equations, equation 1 and equation 2. You have two unknowns. You've got the magnitude of C1 and the magnitude of C2. Two unknowns, two equations to solve. What do we have to do? We use substitution or elimination, right? So in this case, you will end up with the same result as we did with the geometric vectors. However, look at all the amount that I just missed. I'm going to leave it to you. I didn't write down the substitution method, right? You either use substitution or elimination. That's a long process. If you compare to how short our process was for geometric vectors, you can see that in this example, the geometric method is much more efficient. Well, what was given to us, right? What did we have? We had a resultant. We didn't have the initial vectors. If you don't have the initial vectors, the magnitude of the initial vectors, I'd say go use the geometric vector. It'll be much more efficient. This one is really, really long trying to do it algebraic, right? We don't have that much time on a test to do all these things, right? The efficient or the inefficient way, all right? So keep that in your mind, all right? Keep that in mind, all right? I wrote down a couple things in here. What are the unknown vectors, all right? How many initial vectors do you have? Okay, if you get 3 or more, right? Algebraic method. Really easy to add those up when you resolve it, okay? If your unknown vectors are the initial vectors, maybe you should use the geometric method, all right? So go ahead and do these. Try the algebraic method. Find out for yourself which questions are really, really simple to do algebraically and which ones take a long time algebraically to do. Okay, you are responsible to know how to resolve a vector properly. Okay, one of the two methods that you might know. If you only know the method I just showed you, great, there's no decision. You do this method. Okay, if you know both, make sure that you can understand one of them at least. Okay, and do that. Good luck.